Hello and welcome to part 2 of our video series from section 4.4 in our calculus text. In the previous video we got the definitions of concave up and concave down and began to get a feel for what they look like. And so what I want to do next is talk about how we can use the sign of the second derivative to give us information about the concavity of a function. And it goes back to something that we saw in the last section. So I just want to give you a reminder of that. Last time, in the previous section of the text, we saw this statement. If the derivative of a function is positive on an interval, then the function is increasing on that interval. But what happens if I take the derivative of the function in that statement? Then f prime is going to become f double prime, and f is going to become f prime. And so I would get the statement, if f double prime of x is positive on an interval, then the derivative is increasing on the interval. But in the previous video, we noted that if the derivative is increasing, that means the function is concave up. And so we get this statement, that a function is concave up on an interval when its second derivative is positive. And then we can also analyze the second statement that we saw in the previous section. If the derivative is negative on an interval, then f is decreasing, and we can draw the conclusion that if f double prime is negative on an interval, then the derivative is decreasing, but that means the function is concave down. And so we get this statement, that a function is concave down on an interval when the second derivative is negative. And so the big thing here that we want to get out of this is that the sign of the second derivative tells us about the concavity of the function. We're looking for positive and negative second derivatives. And then there's one more term that we want to talk about here. That's inflection point. An inflection point on a graph is going to be a point at which the function changes concavity. So it's either going from concave up to concave down, or from concave down to concave up. So we've got concave up, concave down, and inflection point. Those are the terms that we really want to make sure that we understand from this section. Now let's do a couple of examples to illustrate what we're talking about. And let's pay attention to the similarities between these two examples, but more importantly, the differences between these two examples. And so in this example, I've got the graph of a function, and I'm being asked to identify the intervals at which the function is concave up and concave down, as well as the x-coordinates of any inflection points. So let me look at this graph from left to right. So we start over here on this end of the graph, and what hopefully I can see is that tangent lines, while they're all negative here at the beginning, they're also becoming less negative until we get down here at the bottom, and then they're becoming positive, and for a while they grow to become more positive. And so this function starting off as concave up. But at some point, by the time we get, say, over to here, then we can see that the slopes are getting smaller as I read left to right. So it's going to be concave down. So somewhere in between, there is a point at which the function is concave down. And I'm thinking that maybe that point is right about here. So I'm going to note that this is an inflection point on this graph because it's concave up here and it's concave down over here. And then let's keep going, and we see that the derivatives, the slopes are getting smaller still, but then eventually, by the time we're here, the slopes are beginning to get bigger again. So somewhere in between 0 and, say, 2, there's a point at which the function changes concavity. And again, I'm eyeball estimating this, but it looks like it's right about here when x equals 1. And so we're concave up again. And then one more time, maybe right about here, I switch from concave up to concave down. Again, the slopes are getting bigger as I read left to right here, but now they're starting to get smaller. They're decreasing. And so maybe about here, I'm concave down. And so if I want to try to summarize this, I would say that the function is concave up on, well, minus infinity to roughly minus 4, and then somewhere roughly around 1 to 5.5. And I would say that f is concave down on -4 to about 1, and then 5.5 to positive infinity. And then I have inflection points occur when x is -4, 1, and 5.5. So hopefully we get a sense of, just by looking at the graph of a function, we can judge what the concavity is at any point and where changes in concavity might be occurring. My next example is going to be looking at the same graph that we saw in the previous section, in section 4.3. I'll come back to this table in just a couple minutes. Actually, I should talk about it right now. Sorry. So this is an important set of information to try to get at. So the way to read this is to read across rows. And so if I'm talking about the function, if the values of the function are positive, then I'm talking about points that are above the x-axis. And when the function is negative, when f of x is negative, then the graph lives below the x-axis. The second row talks about the derivative, the first derivative. When the first derivative is positive, we say that the function is increasing. And when the first derivative is negative, we say the function is decreasing. And then lastly, it's the sign of the second derivative that tells us about concavity. So when the second derivative is positive, the function is concave up. When the second derivative is negative, it's concave down. So we want to keep those pieces of information in mind, that the signs of the derivative, the first derivative, and the second derivative tell us different things about the behavior of the function. And it's worth concentrating on this table for a little while.